Hello everyone, today we are going to be learning a bit about calculus, and this is going to be a very elementary introduction to the concepts behind calculus. And in this video we are going to be talking about one of the major branches of calculus, which will be differential calculus. In order to understand what differential calculus actually means, we are going to be talking about a very important concept in calculus, which are derivatives. Now, what are derivatives? So, derivatives are something that, you could say that it's a concept essentially. So, derivatives are a concept that ask us and tell us about the rate of change. Now, you should be asking a question right now, which is, why does this matter? Is it really that important? Why do we have to learn about derivatives, and what importance does this carry? Now, talking about derivatives, let's say that I give you a function, right? So this is our graph, and this is a function. And I want you to find how this function changes, right? So if we have that y is equal to f of x, right? And this is, the function f of x. And I want you to find how y changes as we change x. So how does y change with respect to x? If I told you to find that out, you would need derivatives. So this is essentially the basic concept of derivatives. They tell us about the rate of change of a function as, this input value changes. So that is the basic concept of a derivative. Now, this is important because in physics and, in many areas of mathematics, we talk about change. This is an important concept. Because of change, we have differences in certain things. And in order to analyze this, in order to know the magnitude of certain things, in order to understand things fully, we have to know about the change. For example, velocity is the rate of change of displacement. Well, this is not equal, but the rate of change of displacement, or rather s, which is displacement, with respect to time, is known as velocity. And this is, of course, a very important concept in mathematics and, well, physics as well. Now, moving forward, we have to talk about the formal definition of a derivative. Now, before we talk about this, I'd like to introduce you to the notations that we use in calculus. In differential calculus, we use specific notations for derivatives, and one of those notations is f dash of x, which is also read as f prime of x. And this is the first derivative of the function f of x. Now, I'll tell you what this first derivative means later, but I want you to understand that this is just a general notation for derivatives. Now, after this, there is also another popular notation that is used, which is d of f of x over dx. Or, since y is equal to f of x, we may also write dy over dx. Now, this is read as the derivative of f of x with respect to x, or the derivative of y with respect to x. Now, moving forward to the formal definition of a derivative. dy over dx is equal to the limit of f of x plus h minus f of x over h as h approaches 0. Now, if we just plug in this value of h, we are obviously going to get 0 over 0, which is indeterminate. We can't have that. So in order to find the derivative, now I'll also tell you what this, actually means, what this formal definition means. Let's say that we have a graph of a certain function, f of x. And the graph looks something like this, for instance. Now, what this definition means is that, how we're measuring change, right? You could essentially think of this dy over dx as the very, very small, as the ratio of a very, very small increase in the y, as you know, well, y is obviously equal to f of x. So a very, very small increment in f of x over a very, very small increment in x. So if we have a point over here that corresponds to x, and we have a point besides it, which corresponds to h. Now, although I do say that this is besides it, we have to think of this as, very, very close. So they're essentially almost the same point. Almost the same point. Now, because of this, we get, some difference in the y-coordinate that correspond to these two. And the ratio of that very, very small increase in y over the very, very small increase in x is essentially the derivative. And that is where our formal definition comes in. So the f of x plus h, is the function of, well, if we have, let's say that this h is not a point, but actually the difference between x and a certain point, then f of x plus h is, let's say that this point is a, then f of x plus h is essentially f of a, which corresponds to this coordinate over here. And this derivative is essentially telling us about the rate of change of the function. Now, this is essentially the basic concept behind this. And to put it into practice, let's say, we have that a function f of x is equal to x squared plus 3. Now, by the definition, we have that f of dash of x is equal to the limit of x, or rather h approaches 0, and f of x plus h minus f of x over h. Now, by our function, we have that this is equal to x plus h squared minus 3, and, is it plus 3? It's plus 3. So plus 3 minus x squared minus 3. I've already removed the parentheses that would be here, so we have this. And in h, we have, well, it's h, so yeah. And doing some further simplification, we use this formula right here, a plus b whole squared is equal to a squared plus 2ab plus b squared. And using this, we have x squared plus 2xh plus h squared plus 3 minus x squared. Let me remove this. And minus 3 over h. Now, these cancel out, and this also cancels out, and we are left with this much, of which we will take h as the common. Since h is common, we will take it, and we are left with 2x plus h over h. Now this cancels out, and we are left with the limit as x approaches 0 of 2x plus h. We can just plug in the value of x right here to get that the derivative is equal to 2x. By doing this, we have found that the derivative of x squared plus 3, which was our function, we could also, denote this as df of x over dx, is equal to 2x. So this is our derivative. And let's say that if, by using everything that we've learned, we can deduce that if f of x equals x squared plus 3 was a function that corresponded to position, let's say. So if this was a function that corresponded to position, let's say that this was position, this was respect to time, and we found, that f dash of t is 2t. Then if we have that this is position, we have that since, it is the rate of change of position with respect to time, we have that this is velocity. So velocity is essentially just the derivative of displacement with respect to time. So if this were to be the function that corresponded to the position, then this would be the function that corresponds to the velocity. Using this, we can find the velocity at a point, which would be, relatively impossible, considering the fact that this is a smooth curve. So we would not be able to find, the slope as we would if it were a straight line. So this is all essentially for the, introduction to calculus. I tried to make this video as short and as understandable as possible. And I guess this is it. I mean, I will be bringing more videos, and well, this is just, diving into some of the most basic concepts. And I think this is it. So this was me. Well, thanks for watching to the end. Signing off. Peace.